Alright, for this video we're going to read this article by Josh Haberman, um, Parsing Protobuf at 2 plus gigabyte per second, How I Learned to Love Tail Calls in C. So first of all, we do the routine thing of checking the author. Josh Haberman, I'm an engineer at Google working on the protocol buffers team. This blog is where I write about things I find personally interesting. Opinions are my own and I do not speak for my employer or my team. I am interested in low-level software and how to make it as small, fast, and simple as possible. The software projects I most admire are Lua Just in Time, zlib, and SQLite. I wrote bloating mic bloat face to make it easy to understand what makes binaries big. Bloaty includes its own ELF, Mako, and dwarf parsers in order to deeply analyze the binary. I enjoy learning the dark esoterica that comes from delving this deep into the stack. I created UPB, a small implementation of protocol buffers written in C. This library is used in the official Ruby and PHP libraries for protocol buffers. Some of the things I write about on this blog are far from my expertise. Sometimes my primary motivation for writing a blog entry is to learn enough that I can bring clarity to some topic that I don't understand very well. That said, I check my facts and strive for everything to be correct. Please let me know if you find material errors. Alright, so I do not know what protocol buffers are, so we're gonna go over this. Protocol buffers are language neutral, platform neutral, extensible mechanisms for serializing structured data. What are protocol buffers? Protocol buffers are Google's language neutral, platform neutral, extensible mechanism for serializing structured data. Think XML, but smaller, faster, and simpler. You define how you want your data to be structured once, then you can use a special generated source code to easily write and read your structured data to and from a variety of data streams using a variety of languages. Interesting. So this is probably JSON of all languages. That's what I'm thinking this is, which makes it interesting. So pick your favorite language. Protocol buffers support generated code in C++, C Sharp, Dart, Go, Java, Kotlin, Objective-C, Python, and Ruby. With Proto 3, you can also work with PHP. Example implementation: message person, optional string name, and okay, so some default values. And oh, maybe not, but this is the ordering. Is it the ordering? Or is it the default value? Because this is a string and then it assigns a 3. Alright, so a proto definition. Person John is equal to person.newBuilder, set ID, set new name, that set email, that build, output that new file output stream args0, John write to output. Then using a generated class to persist data. That's what this is. So a generated class, and then for this one using a generator to parse persisted data. So then you have C++ code that does this for a person John, fs stream input, ios and ios binary, john.parse format, parse from stream, reference to the input, id equals john.id. That, so I guess, yeah, that's what this is. It's sort of like, that's what it said exactly. So it's a language neutral, platform neutral, extensible mechanism for serializing structured data. That, if that makes sense. I'm not sure if it's extensible, but that's an important thing if you want to have a protocol. Oh, well, if you have a protocol, then it's already said and done, maybe. I don't know. Alright. Parsing Protobuf at 2 plus gigabyte per second, how I learned to love telcalls in C. An exciting feature just landed in the main branch of the CLang compiler. Using the CLang must tell or attribute must tell statement attributes, you can now get guaranteed telcalls in C, C++, and Objective-C. Alright, so what are telcalls in C? In computer science, a telcall is a subroutine call performed at the final action of a procedure. If the target of a tell is the same subroutine, the subroutine is said to be tell recursive, which is a special case of direct recursion. Tell recursion or tell end recursion is particularly useful and is often easy to optimize in implementations. Tell calls can be implemented without adding a new stack frame to the call stack. Most of the frame of the current procedure is no longer needed and can. Alright, so it's probably the jump to the top of the stack call. So tail calls can be implemented without adding a new stack frame to the call stack. Most of the frame of the current procedure is no longer needed and can be replaced by the frame of the tail call, modified as appropriate. Similar to overlay for processes. But for function calls, the process can then jump to the call subroutine, Producing such code instead of a standard call sequence is called tail call elimination or tail call optimization. Tail call elimination allows procedure calls in tail position to be implemented as efficiently as go-to statements, thus allowing efficient structure programming. In the words of Guy L. Steele, in general, procedure calls may be useful thought of as go-to statements which also pass parameters and can be uniformly coded as jump instructions. Alright. Okay, so as you can see, that's the jump, and the attribute must tell return G. Just jump to that at PLT x86 x85. Perfect. Let me summarize the okay, so what was the question here? For time to time, when disassembling x86 binaries, I stumble on reference to PLT and GOT, especially when calling procedures from a dynamic library. For example, when running a program in GDB. What are these GOT, PLT? PLT stands for Procedure Linkage Table, which is put simply used to call external procedures functions whose address isn't known in the time of linking and is left to be resolved by the dynamic linker at the time. GOT stands for Global Offsets Table and is similarly used to resolve addresses. Both PLT and GOT and other relocation information is explained in greater length in that article. Also, Ian Lance Taylor, the author of Goal, has put up an article series on his blog which is totally worth reading. Linkers and all of that. Alright. So while tail calls are usually associated with a functional programming style, I'm interested in them purely for performance reasons. It turns out that in some cases we can use tail calls to get a better code out of the compiler than would otherwise be possible, at least given current compiler technology, without dropping to assembly. Applying this technique to Protobuf parsing has yielded amazing results. We have managed to demonstrate Protobuf parsing at over 2 GB per second, more than double the previous state of the art. There are multiple techniques that contributed to this speed up, so tail calls equals 2x speed up is the wrong message to take away, but tail calls are a key part of what made that speed up possible. In this plugin tree, I will describe why telecalls are such powerful technique, how we applied them to Protobuf parsing, and how this technique generalizes to interpreters. I think it's likely that all of the major language interpreters written in C, Python, Ruby, PHP, Lua, etc. could get significant performance benefits by adopting this technique. The main downside is portability. Currently, Mustel is a non-standard compiler extension, and while I hope it catches on, it will be a while before it spreads widely enough that your system's compiler is likely to support it. That said, at build time, you can compromise some efficiency for portability if you detect that Mustel is not available. Telecall basics. A telecall is any function call that is in tel position, the final action to be performed before a function returns. When tail call optimization occurs, the compiler emits a jump instruction for the tail call instead of call. This skips over the bookkeeping that would normally allow the callee function G to return back to the caller function F, like creating a new stack frame or pushing the return address. Instead, F function jumps directly to G function call, as if it were part of the same function, and G function returns directly to whatever function called F function. This optimization is safe because F function's stack frame is no longer needed once the tail call has begun, since it is no longer possible to access any of F function's local variables. While this may seem like a run-of-the-mill optimization, it has two very important properties unlock new possibilities in the kinds of algorithms we can write. First, it reduces the stack memory from O(n) to O constant when making n consecutive telcalls, which is important because the stack memory is limited and Stack Overflow will crash your program. This means that certain algorithms are not actually safe to write unless the optimization is performed. Secondly, jump eliminates the performance overhead of call. Alright, so I need to remember what is the difference between call and jump. I wish we had gone to Stack Overflow. Alright, well, for first of all, jump simply jumps to the label that you give it to, which is the memory address as program instructions are stored in memory, while call stores the location where it will return below the call instruction. In this stack, jump to the label and then at the return instruction jump back to what location was stored as said above, below the call instruction. A bit of a difference there as you can see. In my honest opinion, I believe it is fine to simply call functions as that is what the C++ compiler does with functions. But if you must jump, then alright then, just make sure to push the return location or create another label to return to once done executing some code. Here's an example of jumping to other label when done. So start from start, you jump to print the stuff goes here, jump to start label, and then you jump to exit. Or you could just use call. That definitely clears things up. Thank you. I have only started learning assembly this week. It's good to get advice like this. Jump to print. Have you read? Okay. This is ambiguous and very unclear. Jump doesn't set up the stack by pushing the return value, so when you do a read, a bogus return address gets popped off the stack and your code jumps to it. You can fake a call with a jump, but prior to doing jump, you must push the return address on the stack yourself. That's alright. I'm getting a little bit, but not all of it. Alright, this means that certain algorithms are not actually safe to write unless this optimization is performed. Secondly, jump eliminates the performance overhead of calls such that a function call can be just as efficient as any other branch. This is called for branching, or maybe call was assembly x86 call. The call instruction is used to call a function. The call instruction performs two operations. It pushes the return address immediately after the call instruction on the stack. It changes EIP to the call destination. This effectively transfers control to the call target and begins execution there. Alright. Such that a function call can be just as efficient as any other branch. These two properties enable us to use telcalls as an efficient alternative to normal iterative control structures like for or while. This is by no means a new idea. Indeed, it goes back to at least 1977 when Guy Steele wrote an entire paper arguing that procedure calls make for cleaner designs than goto, and that telcall optimization can make them just as fast. This was one of the Lambda papers written between... Where is the Lambda paper? Alright, I guess we wait till this loads. The history of programming languages scheme begins with the development of earlier members of the Lisp family of languages during the second half of the 20th century. During the design and development period of Scheme, language designers Guy L. Steele and Gerald J. Sussman released an influential series of MIT AI memos known as the Lambda Papers. This resulted in the growth of popularity in the language and the era of standardization from 1990s onward. Much of the history of Scheme has been documented by the developers themselves. This is interesting. So the list of papers are Scheme and Interpreter for Extended Lambda Calculus, Lambda the Ultimate Imperative, Lambda the Ultimate Declarative, Debunking the Expensive Procedure Call Myth, or Procedure Call Implementations Considered Harmful, or Lambda, the Ultimate Go-To, The Art of the Interpreter, or the Modularity Complex, Rabbit, a compiler for Scheme, Design of Lisp-based processors or Scheme, a dialect of Lisp, or Finite Memory is Considered Harmful, or Lambda, the Ultimate Opcode, Compiler Optimization based on viewing Lambda as rename plus goto, Design of a Lisp-based processor. Alright. I guess the influential papers that changed the standardization and not sure what exactly I'm following here, but let's just keep following. Telcall optimization is not even new to Clang. Like GCC, the many other compilers, Clang was already capable of optimizing telcalls. In fact, the must-tell attribute in our first example above did not change the output of the compiler at all. Clang would have already optimized the telcall under is this flag or -02. What is new is the guarantee. While compilers will often optimize telcalls successfully, this is the best effort, not something you can rely on. In particular, the optimization will most likely not happen in non-optimized builds. So if we follow this, we have void and then g, that's the function, and then return this, whatever you define it, and then if I have my beautiful pink thingy, we will have push RBP what is RBP in x86? So RBP is base pointer. Just write this down. Okay. Alright, good enough. And this RBP. Probably have to change the default is register. No. And then there was more. And then stack pointer, I believe. Yeah. So dword pointer register base pointer -4 bytes EDI what is the actual purpose and use of the EDI and ESI registers in assembler? I know they are used for string operations for one thing. Can someone also give an example? So SI is source index, DI is destination index. As others have indicated, they have special uses with the string instructions. For real mode programming, the ES segment register must be used with DI and DS with SI as in move stack SB stack base. Is that what it is? All right. Okay. Here. Okay, so moves, move SB, move SW, move SD, move SQ, move data from string to string. Oh, interesting. So opcode A4. Then you have your instruction operation set 64-bit mode and that for legacy mode move byte from address that to there. Alright, so I need to keep it abstract because I don't understand all of this, but as you can see there's a call function here instead of jump. And because of that it shows that here we don't have that optimization. Alright, so here the tail call was compiled to an actual call, so we are back to ON stack space. This is why we need must tell unless we can get a guarantee from the compiler that our tail calls will always be optimized. In all build modes, it isn't safe to write algorithms that use tail calls for iteration. It would be a pretty severe limitation to have code that only works when optimizations are enabled. The trouble with interpreter loops. Compilers are an incredible piece of technology, but they are not perfect. Mike Paul, author of Lua Just-in-Time, decided to write Lua Just-in-Time 2x interpreter in assembly rather than C. And he cites the decision as a major factor that explains why Lua Just-in-Time interpreter is so fast. He later went into more detail about why C compilers struggle with interpreter main loops. Wow. Lua is this what it is? Is that him? Mike Paul? Is Mike? That's interesting. Lua just-in-time interpreter is fast because it's written in assembler. It keeps all important state in registers. No sync compiler manages to do that on x86. It uses indirect threading, aka label goto in C. It has a very small L cache footprint. The core of the interpreter fits in 60K. The parser generates a register-based bytecode. The bytecode is really a word code, 32 byte per instruction, and designed for fast decoding. Bytecode decode and dispatch is heavily optimized for superscale CPUs. The bytecode is type specialized and patched on the fly. The dispatch table is patched to allow for debug hooks and trace recording. No need to check for these cases in the fast paths. Using non-number tagging for object references, this allows unboxed FP numbers with a minimal cache footprint. For stacks and arrays, FP stores are auto-tagging. It inlines all fast paths. It uses special calling conventions for built-ins. Tons more tuning in the VM. And the just-in-time compiler has its own bag of tricks. Alright, but this is interesting. Maybe we go over Lua at some other time. Alright, so, and we also read this, but he later went into more detail about why C compilers struggle with interpreter main loops. Oh, that's what it is, because yeah, the Python loops, for example, that I know are extremely slow. His two most central points are the larger a function is and the more complex and connected its control flow, the harder it is for the compiler's register allocated to keep the most important data in registers. When fast paths and slow paths are intermixed in the same functions, the presence of slow paths compromises the code quality of the fast paths. Alright, so let's just write that to fast paths, slow paths. Alright, so the larger function is the more complex its control, the harder it is for the compiler's register allocator. Register allocator. These observations closely mirror our experiences optimizing protobuf parsing. The good news is that telcalls can help solve both of these problems. It may seem odd to compare interpreter loops to protobuf parsers, but the nature of the protobuf wire format makes them more similar than you might expect. The protobuf wire format is a series of tag/value pairs where the tag contains a field number and wire type. These tags act similarly to an interpreter opcode. It tells us what operation we need to perform to parse this field's data. Like interpreter opcodes, protobuf field numbers can come in any order, so we have to be prepared to dispatch to any part of the code at any time. The natural way to write such a parser is to have a while loop surrounding a switch statement, and indeed this has been the state of the art in protobuf parsing for basically as long as